In order to solve quadratic equations, we really do need to deal with squares and square roots. So we take our perfect squared, and remember, a perfect square occurs when you have a number times itself, like this. So we have our perfect squares, 1 through 25, and I highly recommend that you memorize these. And the reason that you want to memorize these is because if 1 squared equals 1 and 14 squared equals 196, we can use that information to take the square roots of numbers. So 1 squared equals 1, that means the square root of 1 is 1, and the square root of 4 is 2, and the square root of 196 is 14, etc. So you'll want to learn these to make taking squares or square roots easier. So if you'd like, you can take some time, pause the video, write these down. Okay, so moving on, we want to simplify perfect square roots. And again, this is much easier if we have our squares memorized. So 100 is equal to 10 squared. And so the square root of 100 is 10. 25 is 5 squared, so the square root is 5. 81 is 9. Square root of 1 is 1. Square root of 49 is 7. Square root of negative 81. We're in the real number system. And in the real number system, we don't have any perfect squares that are negative, because if I take 9 and I square it, I get 81 because it's 9 times 9. And if I take negative 9 and I square it, I get 81 because negative 9 times negative 9 is a positive 81. So the square root of a negative number does not exist in the real number system. In order for this to exist, we have to move into a different number system called the complex numbers, and we're not there yet. $400, well, we look back at that. 20 squared is 400, so the square root of 400 is 20. 121 is 11 squared, so the square root of 121 is 11. Square root of negative 4, again, we don't have negative perfect squares, so it does not exist. Now, if the negative is hanging out front of the square root, that's allowed. What we do is we just carry that negative over. It just hangs out. And then we take the square root of 4, which is 2. So if the negative is outside of the square root, it carries out. If it's inside of the square root, it does not exist. Those are perfect square roots. But what happens if we have non-perfect squares or unknown perfect squares? Well, my best way to figure these out is we first make a factor tree. So 75 is 3 times 25. And 25 is 5 times 5. Now, identifying the perfect squares, you have matches. 5 times 5 is a perfect square. The way I like to look at it is anybody that can pair off gets to go out. They go out on a date. So if you have a match, you get to go out. If you do not have a match, you don't get to go out. You have to stay in. So if you match, you get to go out on a date. If you don't have a match, you have to stay in or stay home. So let's look at another one. 300 is 3 times 100. Now, if you get to this point and you recognize that 100 is a perfect square, you can go ahead and take the square root of 100, which is 10, and bring that outside. Or if you don't recognize that, we can continue to factor this. Okay, I have a pair of 2s, they match, they get to go out. I have a pair of 5s, they match, they get to go out. So 2 gets to go out and 5 gets to go out. But then 3, again, doesn't have a match, so he has to stay home. Well, that's great, but what do I do with this? I brought out the 2 and I brought out the 5. I need to put those back together. So I multiply 2 times 5, and I get 10 times the square root of 3 is my final answer. 784, I don't know if that has any perfect squares in it or not, so I'm going to start factoring it. I divide it by 2 because it's even. So I get a 3 and a 9 and a 2, which is also even. And I get a 1 and a 9 and a 6, which is also even. So I get a 2 and a 9 and an 8 and a 2 and a 49 and a 7 and a 7. I have 1 pair of 2s, I have 2 pairs of 2s, and I have 1 pair of 7s, and you'll see that there's nothing left over. Everything matches up, so everything gets to go out, and my final answer for this is 2 times 2, 1 2 from the first pair, 1 2 from the second pair, and a 7. So I have 2 times 2 is 4 times 7 is 28. So 784 is a perfect square. It is 28 squared, so the square root is 28. Last example, we have 720, and it doesn't matter how you break them up. Just remember that only the ends of your little branches can count. So as we go through this, the 10 became 2 times 5, so it's gone. 72 became 8 times 9, so it's gone. 8 became 2 times 4, and 4 became 2 times 2. 9 became 3 times 3. So these numbers no longer count. It's only the end of the branches that we want to look at. Okay, I have a pair of 3s, a pair of 2s, another pair of 2s, and they don't have to be on the same branches. If they match, they're fine. And then some lonely little 5 that's going to have to stay home because he doesn't have a match. So 1 2 from this pair, 1 2 from this pair, 1 3 from this pair, and a 5 that has to stay home. 2 times 2 times 3 is 4 times 3, which is 12, times the square root of 5. Okay, square rooting fractions. When we look at a square root of a fraction, we have the square root with the fraction underneath, and that is the same thing as the square root of the numerator over the square root of the denominator. So you take the square root of each of them individually. The square root of 1 is 1, the square root of 9 is 3. Square root of 25 over the square root of 81. Square root of 25 is 5. Square root of 81 is 9. Square root of 9 over the square root of 4. Square root of 9 is 3. Square root of 4 is 2. So you just look at each individually and take the square roots of them. Don't let the fact that it's a fraction trip you up. Oops. Okay. Lastly, if we have the square root of a decimal, 144 is the square root of 12. or sorry, is 12 squared. So the square root of 144 would be 12. But this isn't going to be 12. It's actually going to be 1.2. Now, if it all else fails on these, use the calculator. That ends our video on section 1 for unit 11, taking square roots. If you are in my current class, you'll need to take the quiz available on the website. And that's the in-grade website. If you're not in my class, I hope this